Our sample problem here says an electron enters a region of uniform electric field with E equaling 50 newtons per coulomb. So this electron enters the field with an initial velocity of 40 kilometers per second, directed the same as the electric field. What is the speed of the electron 1.5 nanoseconds after entering this region? All right, so we have an electric field. I'm just going to give myself a direction for this electric field. This electric field is pointing to the right, just because I chose that. It has a magnitude of 50 newtons per coulomb. In my picture, the direction is I hat. This electron is moving with an initial velocity of 40 kilometers per second. And it tells us this velocity is directed the same as the electric field. Okay, we want to know this V final. How fast is this electron traveling after 1.5 nanoseconds? We're trying to, such a short time, to stay out of the relativistic ranges. Okay. Now the equation's fairly easy. Our electric force is Q times E. That's going to equal MA, because we're only talking about this electric field, slowing it down. We know the electric field, we know the charge, we know the mass, we know the time, we want V final. Now, I highly recommend just conceptually thinking through what you expect to happen. Do you expect this electron to speed up or slow down? Now, the reason I ask is because we want to make sure we're getting an answer that represents what we're expecting. So electric fields are created by some sort of positive charges. The electric field lines leave the positive charge and point towards negative charge. So this electron traveling the same direction as the electric field is essentially heading towards some sort of negatively charged object. So, knowing that, is it going to speed up to get there faster or slow down? Well, I expect it would slow down. Electrons are repelled by other electrons. So I expect it to slow down. Meaning we should get an answer for V final that is smaller than V initial. Okay, so we have a time, we want a V final, we have a V initial. So in terms of our kinematic equations, to relate those to acceleration, V final is going to be simply V initial plus AT. We already have V initial, we just need to figure out A. Now, by the way, the reason I know I can use kinematic equations is because this electric field is constant. If the electric field is constant, this acceleration is also going to be constant. The charge of the electron is not changing. It's not writing well. Let's try that again. 1.6 times 10 to the negative 19 times the 50 over the mass. And again, the charge and the mass are on the front cover of the test notes. For an electron, the charge is the fundamental unit of charge. Okay. Now, as long as we remember the negative sign on Q, we are getting a negative acceleration, which is going to be opposite the velocity. But if we didn't remember to put the negative sign on Q, which I've seen many times, that's why I mention it, then we would get a positive value. And if we didn't think about the direction, then we would not know to expect a smaller speed or a slower speed. So I'm putting in V initial, 40 kilometers per second. I need to put in 10 to the 3 for the kilo part. We just calculated our acceleration, which is in meters per second squared. The time, 1.5 nanoseconds. My calculator is telling me this, and even more digits, but I cannot even be this accurate. We have 2 sig figs. I'm going to go ahead and write this in kilometers per second again, since that's how they gave the initial speed. So this 6 would round to a 7. So the speed of the electron would now be 27 kilometers per second, which is less than 40. It did slow down. So that's just a good check to make sure the answer makes sense in terms of at least slowing down versus speeding up.